Before I start, I was here last year, almost a year ago, when exactly in this hall we celebrated the Einstein field equations, which were developed fully in 1915 for the first time. And in fact, that was what the whole meeting was about, talking about that. And it was an enormous honor to be there then. It's a huge honor to be asked to give a talk here. I feel a little bit trepidatious about it, because I don't know if I really fit in this remarkable setting here. I want to talk to you a little bit about Einstein first, because that's what you're seeing on the screen. And I think conversations like I'm going to make now must have happened in this hall between Einstein and Planck. Or maybe not in this hall, but it's certainly in this building. That was built, I believe, that's where Einstein had his first institute when he was brought to Berlin, is right in this building. And so I think Planck advised him not to work on gravitation. Why? Because it was already a well-established idea. There wasn't going to be anything really brand new going to come out of it. I mean, you can read about these conversations. And Einstein was insistent that there was something he had to work on. And what he had to work on was that Newton's theory, which we all learn. I mean, all of us, even when we go to high school, we learn about it. As a force, it's between masses. It goes as 1 over the distance squared. Does work exceedingly well. It gets people to satellites. It makes us understand why we stick to the ground a little. Not completely, but a little bit. And it is a theory that works all the way up to your cell phone. Or your GPS. No, the fact that you don't know quite how to use GPS without general relativity. That's a well-known thing. You would be in the wrong place if that wasn't corrected for relativistic corrections. But that is a small thing. What Einstein was worried about was different things. He was worried about two things that he knew he had to solve. And they were fundamental in terms of the way you think about the physics of gravity. One was that you could not have information travel at infinite speeds, like it was implied by the Newtonian theory. And that was already quite clear to him from special relativity from 1905. And the other thing is that you had to somehow have a way of dealing with the theory working for large velocities as well. And he knew that both of those things were not incorporated in the Newtonian theory. And so he worked very hard on it. And so what he did is, and I can't give you the theory, but I want you to at least understand what he did. And what he did is that he imagined that there was no longer a gravitational force. Rather, what was happening is sort of what's in this picture, but you will have to understand first what that picture is doing. And that is that you lay out, in order to understand what Einstein did, is you have to lay out all of space like a giant coordinate system. In the United States, we have jungle gyms. Kids go in jungle gyms, and they're all three-dimensional rectangular structures with all sorts of posts, all rectangular. And the thing you have to add, and you put this into space, and now you add to that, everywhere, at every intersection of every rod, you put a clock. And that's the way Einstein wants you to start thinking about space. And now, here is what's in that picture, and depicted in that picture, is in fact the way he thought about it. Here is part of that jungle gym, or that layout of space, which was completely regular looking before you put the sun into the business, and you see a curvature in space that has happened here. And there's the Earth, and another curvature right there. And what has happened is these masses that you've put into this thing have distorted space. They've distorted the way the jungle gym looks, and they also have distorted the way the clocks keep time. So both things are important. And once you have that, you begin to get a completely new conception that he had. And the conception was that the distortion of space made by these masses would then cause the masses to move in such a way that the best, closest path to a straight line is a curved path. So what he has done in one fell swoop, he's converted the whole idea of Newtonian gravity into a geometric theory. And that geometric theory then had in it the notion that there would be gravitational waves. And that is the next step in this, and I want to spend a little time on that, is that what the gravitational waves are they come from sources very much like they do in electricity and magnetism. Accelerated masses make gravitational waves, but not every shape of acceleration does that. Non-spherically symmetric shape of masses do that. For example, things that crash together, that will generate gravitational waves. Things that expand uniformly and contract uniformly do not make gravitational waves. They don't. They just everything cancels in them. And so the thing is that that's why it's called non-spherically symmetric accelerated masses. And the kinematics of these waves are that they move at the speed of light, just like electromagnetic waves. And they also come and do this to space. This is what they do to space. And here the way you want to imagine this is that this is a picture that's going to start moving in a second. You're standing right here where that red dot is. And this is a set of masses you've laid out in space. Let's say far outer space, so you're not near other masses, and you turn off gravity for a second between the masses, so they just sit there. And now a gravitational wave comes along, and it does this. This is what it does to those masses. What it does, and you want to analyze this pattern a little bit, the reason why is because it's the basis for the detection. See, what happens is this. You look at this thing, and you'll notice that there's a stretching of space in one dimension, while there is at the same time a compression of space in the other, and they keep alternating. So you have this thing which is going squish like that, expanding, and conversely those two roles change. The wave is transverse. The wave is coming out at you or going into the board, or into that picture. And there's a very special property of this thing that you'll notice. You'll notice that the two dots, let's say these two, let's follow those two, near you, are moving very little. But the two dots that are as far away as possible from you, that one and that one, are moving a lot. And that then that turns out to be at any one moment a motion that is described, the entire motion is described by a thing that has constant strain, named the change in the space between things divided by their separation is the same all over that picture at any one moment. Of course, it's time changing right now. And that's the key. The thing that is very much like the electric field in electricity and magnetism, that the B field or the electric field, in this case, in the Einstein gravitational waves, is the strain. And you capitalize on that to make a measurement. So that's something I want you to remember, otherwise you will not understand exactly what follows. Okay, so Einstein in 1915 wrote this paper we all celebrate. We didn't celebrate the papers in 1916 and 1918. They were not part of the discussion we had here a year ago. But they were specific applications of the field equations, which were ones where he tried to show that there were new applications that came out of these very much more complicated equations. And one of them was, indeed, gravitational waves. He makes a significant error in the thing that's not important to what I'm about to tell you. And he fixes that in 1918. You have to read both papers together if you want to understand the history. But he makes a very interesting statement here. And you can read German, I can too, but I don't speak German as well as I can speak English. So I have to give this lecture in English. But at the end of the paper, he says this quantity, he talks about, you see that this quantity, which happens to be a quantity that relates the motions in the source to the strength of the gravitational field. He says, he goes through a whole long thing and he says, look, this quantity, and so you see in German, you can read in German, in any case one can think of, A, that's this quantity, will have a practically vanishing value. What he says at the end of this paper is that this will never have any influence, this gravitational wave business will never have any influence in physics. It will never affect anything of any consequence. And that's the thing which is quite dramatic that he says in the paper. And you have to think now, and I'm a little presumptuous to be sitting here in the Harnack house and making believe I'm Einstein, but I'll have to do it because these papers have not been found. These are papers which you would have found in his notebooks. What he might have done to make that statement is, for example, he might have taken the idea of having two trains colliding with each other. And now, here I have to use an equation, but it's an easy equation. H is the strain. It's that change in length divided by the length. And in the most simple-minded way, you'll eventually get the following relationship between H and the physical properties that you want to get. So you want to talk about what's going on in the system. And so you see, for example, what's in here is G, which is a Newtonian constant. It's a number. The mass of the system that's doing the motion divided by the distance you're away from it divided by the velocity of light squared. That quantity is the dimensionless constant of the gravitational constant. And what it is, for example, you and I are living right now in a place where that number is about 10 to the minus 10. It's tiny. We're in a very weak field. When we get to the end of this talk, we'll be dealing with things where that number is of the order 1, which is really quite spectacular. And by the way, the Einstein field equations still seem to work over that huge range, dynamic range. And what's the next step is just what this is the velocity of the motion divided by the velocity of light. This quantity allows you to make an estimate for how big will be the strain in the gravitational wave. If you think for example, let's take the example that I took. You take the two trains, they weigh about 10 to the 5 kilograms. In Einstein's day, in 1916, they might have gone at 100 kilometers per hour. It's not important exactly. They may have collided in less than a third of a second, maybe something like that. You have to have some time when they collided. And the radiation you have to be a distance away enough from this system so that Newton isn't the dominant thing. You have to go out in a place where the wave becomes important. So you can see that over other things that in the field. That has to be a one wavelength away. It's about 300 kilometers. And then you calculate h, and you get a number which Einstein must have been horrified at, 10 to the minus 42. That's a number that's really impossible to measure. Okay? I mean, and this was part of what must have been behind his statement. The other thing is that he might have very well thought, and I know he did, because you can see in the later writings, he thought of that maybe you could see this in a telescope. And you look two stars going around each other. They're a system that that'll radiate. That's not spherically symmetric. And what kind of numbers, if you see them could you see in a telescope, not measure the h directly, but rather could you see the system lose energy, get closer and closer together and go faster and faster? And he made a number, and here's the number he must have made. He takes a solar mass for the star, which is what our sun waves. And the orbit for these two things would be a day. There are things like that he must have known about. The thing he didn't know about is how big the galaxy was. But 10 kilo light years is about right. And you put that in for these numbers, exactly right up here and again, into this formula, and you'll get a number that's about 10 to the minus 23 for h. That's still tiny. But it turns out that's not so tiny you can't think about it. Okay, and we'll see that as we go on. And with a period of half a day. But then the thing he would have wanted to do is look at this thing. How long would it take, let's say before those stars got a half closer to each other, half distance that they are apart now, closer to each other. And it would take in 10 to the 13 years. That's much, much longer than the age of the universe, which he didn't know about. But it's a long, long time. So with those examples, I'd love to see where he really did this in a notebook and where people are looking for this, right, in Jerusalem and other of the Einstein papers. But it turns out that, yes, he was right, that he could not, in his time, have imagined this. Now, things changed. And what has changed is, first of all, we've learned a lot more about the universe. And we also learned a lot more about how to do technical things like this. And both are critical to this business that now there has been a detection of it. But before we get to that, I think one of the most important steps in this whole step is something done by Russell Hulse, who was a graduate student, and Joe Taylor, who was a professor both of these were at the University of Massachusetts. They're now at Princeton. One is in Plasma Lab, the other one is a professor at Princeton. And what they found was a most remarkable system. And the system they found in a radio telescope experiment, and they did this by, now mind you, this is one of these wonderful, ingenious things people can do. All they heard, or all they saw, was pulses from a star. This star right there. And that star puts out 17 pulses per second. It's a pulsar. It's a neutron star. And one way to think about how outrageous that star is to think if you cut a teaspoon of that stuff that it's made, which is pure nuclear material, you couldn't lift it because it would weigh 10 to the 15 grams. 1 teaspoon of it weighed 10 to the 15 grams. So 10 to, a billion tons in 1 teaspoon. Just imagine that. That's the density of that stuff. So this thing is spinning. It's a pulsar. And what they were seeing is they were seeing this thing going around. They knew what it was by this time, and they noticed something very interesting about it. But they noticed that it was sometimes going a little faster than 17 pulses per second, and sometimes a little slower than that. And it was doing that with a period of about 8 hours. That's what they saw. And so they thought about it, and they said, well, this is a binary system. And they eventually, because they couldn't see anything, all they did were radio telescopes, they then hypothesized that what was going around was another neutron star, and these two are going around each other like this, just like the experiment that I described to you a second ago that Einstein might have calculated. But this time, they saw something that was due to gravitational waves. And the thing that they saw, because they watched this thing for about 20 years. People are still watching it now. But they saw it in 1973, and they plotted all sorts of things. They got the masses of those stars. They got, for example, they got a very important relativistic correction that's made in motion that Newton didn't have right. They measured that very quickly. It's called the perihelion advance at Mercury. Let's go into it, otherwise we'd be here all day. But the thing is, this is the thing that was a telltale to them. What they found is that these stars were getting closer and closer to each other and getting faster and faster. In other words, the period of this to go around once was getting shorter. And this is the length of period in seconds, and this is the epoch in time. In other words, every time they looked at it, and the dots they have, every time it went around once, they put it down. And then these dots are the actual values they got for the data. And this curve that goes through it is not a fit. It's what Einstein's theory predicted for the amount of loss of period, thereby also the energy left that leaves that system due to gravitational waves. That was the first real discovery of gravitational waves. It was an indirect measurement, but profoundly important. Because we now then knew, in fact, the people on the ground, and people even in space, know what to look for. Okay, it's very important. It was, and it won the Nobel Prize in 1993 or 2003. Who knows that? 93. Yeah. Okay. Now, the next step in this thing is that in about 1957, there was a huge conference of all the people doing relativity in the world at Chapel Hill, North Carolina. And the reason they did is that the attempt was being made to bring general relativity back into physics. It was probably a branch of mathematics. All of them, for the middle of 1920s till about then, it had been mathematics, and people were trying to say what was real, what could be measurable. That was one thing. And gravitational waves, as Martin said, were continually being debated. In fact, Einstein changed his mind once or twice about whether they existed. And so did many other people. And so the first person, along with John Wheeler, who attempted to try to measure gravitational waves. John Wheeler and Weber invented this idea together. And Weber was a professor at the University of Maryland. And the idea was there's Weber soldering some sensors on a great big bar. There's a huge bar of aluminum. And the idea was that a gravitational wave would come along, a fast one, one that had a very quick pulse. It would excite that bar to sing, just like as though it was a xylophone, and you bopped it with a hammer, and you could then listen to it after the wave had gone by. So you get a bop, and then try to listen to it, and the thought was that would be a way to detect gravitational waves. It was the first real experiment to try to do this. And it turns out that's where the story that Martin was telling comes in. A lot of people in the world tried to do this too after Weber published that he had measured gravitational waves in 1969. A whole bunch of people. And it was the best group, I think the group that did this, the best of all, was the group here in Garching. The group that Heinz Billing started in Garching got, I think, the best zero. In other words, he nailed it. There are other people who didn't nail it as well. They nailed it completely. There was nothing to be seen. Weber was not seeing gravitational waves. They didn't say what he was seeing, but he wasn't seeing those. And so that time is when I was teaching that course that I'm not going to repeat, but it's an important thing in my life that something came out of a course that you teach that was very, very important for research. That's an interesting thing that happens. Once in a while, teaching gives you ideas that you don't get normally just standing around, okay? And these are people who tried to do the Weber experiments. And the idea that grew up in that course was the idea of timing light as a way I could not explain, as Martin said, I could not explain to the students in my class. And by the way, you're absolutely right. What I knew about general relativity was very, very little. And in fact, was so little that I was always terrified that I will be not a day ahead of the students, I'd be a day behind the students. That is more likely what would happen. And I just didn't know the mathematics well enough. But when we got to this idea, they wanted me to explain to them what was Weber's experiment. This was before he made the publication. I couldn't explain it to them. And what I said, that's when this Gedanken Experiment was invented. The idea was so very, very simple. Once you had that picture that I showed you of the dots, you would have the idea yourself. It's not very complicated. Why don't you just measure the distance between those dots by sending light from one to the other? That's about, what you do is you time light. But you have a clock and a mass and a clock and a mass. You send light from one to the other, look at the time when it left, look at the time when it gets received, and you can say that if there's a gravitational wave there, it'll change. And that's exactly what happens. It's about as simple-minded a calculation as you can do in general relativity. It's not even general relativity, it's special relativity with a little extra So it turns out to be so simple. Much, much harder is to try to explain how a bar interacts with a gravitational wave. I couldn't do it. Couldn't understand how that worked. So here is the idea as a thing, so you can help to understand it yourself. Here's the idea. What you're doing is you're sending light to a beam splitter. You're splitting it. What you see is the electric field in the light. The red means that's where there's power in the wave. Here's a mirror, like that distant mass you saw, and there's another distant mass over here. And this is where you were standing, that dot, red dot. And there you notice no light going to the photodetector. It's canceled. You made it so that there's exactly equal times in these two things. And now you begin to move, just like those dots. I made them move, these guys move, and you'll notice light goes to the photodetector when you spoil the fact that there's no longer exactly equal time. These two waves don't cancel anymore. So what happens is you lay a trap for the gravitational wave, which is coming down from above. What it's doing is it makes the distance between those end masses change. One contract, the other expand, and it changes it so that you get light to the photodetector. It's very straightforward. It is. So, and it turns out though that the trickery comes in when you begin to look at how well you have to do. Okay, and that's where the iron comes into the fire. So the people who were working in this business at the time, and when Weber was doing this, he was measuring strains, we now believe, of about 10 to the minus 14, which are much too big. In fact, people very rapidly pointed out to Weber that if he was right, he would wipe out the entire galaxy into gravitational waves in a million years. In other words, all the rest mass in the universe would go, in our galaxy, would go into gravitational waves. It was a very serious problem. But there was a huge argument. Let's not go into it all. But if you had asked me questions about it, the piece of history that's associated with that is really fascinating. Anyway, so here's the issue, and here's where things get tough. So, okay, people like Kip Thorne and other theorists, Kafka here here who was working with Billings, they made numbers for possible sources, and they said you've got to be able to get down to measurements of strain of 10 to the minus 21. And if you have, and this is for LIGO anticipating it, if you have a 4-kilometer arm, the distance between those dots is 4 kilometers, you have to measure 10 to the minus 18 meters. And let me give you, some of you who are in the humanities, a feeling for what that means. Those of you in hard sciences don't have to look at this, but it's a mixed audience, and I do want to have to drive this point. And that is that you start with a meter, and now what you're going down to 10 to the minus 18 meters. What is get some sense, some feeling for that. And well, okay, but you divide by 10,000, you wind up with 1 hair. That's about the diameter of your hair. Okay? So you divide another 100, and you get down to about the wavelength of light. It's not the light you see. That's half a wavelength. Half a micron is about the wavelength that you see best, green light. But that's still something you can deal with. And you can even deal with the next division by 10,000. So you're down to about the size of an atom. And you and your children and everybody can get an idea of the size of an atom in your house by just getting a medicine dropper, make a medicine dropper, put some oil in it, and have a big tub full of water, and measure the volume of the medicine drop, the drop that comes out of the medicine dropper, call it a few millimeters, and you drop it into this tub, and you look at the area of the water, the area of the oil floating on the water, and then from that, if you want to make the same volume as came in the drop, you find out you can get the height. It's a very straightforward experiment you can do, and sure as hell, you will find it's of the order of it's a few times 10 to the minus 10 meters. It's a very simple experiment to do. It's just a gorgeous thing to do yourself. But then it gets to the point where you can't do anything anymore. You're stuck. You're stuck with people telling you things. And so, all right, you get another 100,000, you get down to the nuclear diameter inside of an atom. And then finally, you're still there. You're not there yet. You have to divide by another 1,000. And that's 10 to the minus 18 meters. And that's a trick. That's not easy to do. And so here are the people who made it happen. In other words, the idea was simple enough, and other people, by the time this happened, had also had that idea. It was not just my idea, Martin. Other people had that idea. And so what happened is the thing that was done at MIT was I had some ideas to get to that type of sensitivity. And let me sort of tell you what it was. We have this factor of 10 to the 12 that happens twice. The first factor of 10 to the 12, and this is in the technology. You have to use light, which has a wavelength of 10 to the minus 6 meters, to measure 10 to the minus 18 meters. Right? That means you have to somehow use light reduce its ability, make the ability that you can do it to 10 to the 12. Well, 10 to the 12 times better than the wavelength. That's your first trouble. And then in the end, you have to also do something to make sure the things you're looking at don't shake. We'll get to that. So the first 10 to the 12 is how do you get there? And that's what all these people were helping doing. And here was the basic idea. This is the thing that started at MIT, but it was by no means the only place. Instead, you had two ideas that got you part of the way to the 10 to the 12. One was using a laser, and that gets you a goodly way there because you have all these photons that are in the same state, and you get a factor of about 10 to the 10 for that alone. Not quite 10 to the 10. The other factor is you bounce the light back and forth, and that's what was done in this thing 100 times. That was done with one technology here, and that gets you another factor of 100. Now, the people who did this better than anybody in the world and did it first were the people up here. This is the group, Billing's group in Garching. Here's Heinz Billing, but you notice what he's got. He was also working on bars, and he was made of Weber bars, I told you earlier, but they thought this idea was a good idea, and all of these people contributed vastly to this. For example, of them, everyone, I won't only say something, he contributed an idea that you use cavities to look at stabilizing cavities. He invented something which this man also invented, this, we'll get to him in a minute, he invented something power recycling. We'll get to what that means in a minute. He saw what the problems would be in the optics. He decided that all the things had to be floated. Every bloody mirror, everything in the system had to be floating. You couldn't put it on a table. And Frau Schnupp had a wonderful idea of how to not put certain kinds of things into the interferometer. So it turns out that group built the 3-meter system way before this thing at MIT got even close to finished. And they showed they showed some of the ideas were right. They also showed some of the ideas were wrong. And then they built the 30-meter and showed that the scaling laws worked. They made fundamental progress in this whole business. Now, a little bit after they had got their 3-meter running, it turns out this group in Scotland, and this is Ron Drever, who is another recipient of all these prizes that Kip and I are, started a group. He also had been working on bars, different kind of bars, and he also got the idea of you might want to do lasers. I mean, he got it from the Germans as much as from other people. And then there were people in his group that have developed ideas. And for example, another idea that became very important between Ron Drever and Brian Mears is the idea, I'll show you that in a minute, of putting in another mirror into the interferometer, which I'll describe to you. The idea of something called signal recycling. And well, these people are still busy with something now called LISA, which we'll talk about near the end. And they were very busy with making geo work. So this was a major group effort, and giving it all to me is crazy. It's not just crazy. So here is now the interferometer, and it's been gussied up somewhat. It's been made so it could do this. And let me show you what's in it. Here's the things you saw in the animation. You saw the laser. We saw the beam splitter, which splits the light. Half of it reflected, half of it transmitted. There's that far mirror, and there's that far mirror. So those are the things you know about a little. And there's the photodetector. So there's some new mirrors in here. These mirrors, for example, make the light bounce back and forth many times, several hundred times. This is a Fabry-Perot cavity, that's what it's called. And so that's the way you get that extra factor of bouncing on these mirrors, the gain you get of that. But there's some new ideas in here. This idea is a fairly simple one. When you have no light going to the photodetector, let's say all the light is going somewhere, you send the light in, what it does, it all goes back to the laser. That's where it goes. When that's where you arrange this thing so equal times in all of these things, both equal times in these two arms, then you find out you put no light here. It turns out the light has to go someplace, and when it does, it goes back to the laser. And this idea, both by Schilling and Drever, was to put another mirror right here. A very clever idea. The idea was to take that and what they call in the radio trade, match the laser to the interferometer. Make it so that all the light that comes back from the interferometer is reflected back into the system, as well as the light that would have been reflected by the laser from this side of the mirror. In other words, make it so there's no light reflected back to the laser, all of it. Everything that the laser puts out is put into the interferometer and stays there. And that builds up. For example, if you had 25 watts of light here, you might have 500 watts of light circulating in this. And you might have hundreds of thousands of watts of light circulating in these arms. That's how you build up all of the sensitivity. And this fancy mirror, this one, that's something we have only just used recently. It's the idea of signal recycling. It does something very tricky. I'll just tell you what it is. You can ask me about it if you care. But what it does is it goes in front of the detector, mind you. It blocks the light to the detector. But what it does is it allows you to tune the interferometer spectrally. You can make it so you can make it narrow, sensitive to narrow bands or wide bands. You can tune the interferometer with it. And that's a very elegant scheme, and that has made a lot of difference for GEO, for example, which has, okay, so now here's what happened in the United States. In the United States, we had to make a proposal to the NSF once this thing got going. And the man who made the proposal with us was Robbie Vogt. He was the very first director of LIGO. This is after Thorne, Drever, and I tried to make the project run. This guy got us organized. And he did something really quite important. He helped us write this proposal, which then did get the money to get LIGO going. It's one of the perils of Pauline that you were talking about. And he was the first guy who helped us get around one of the big hurdles. And then he did one thing very intelligent. When you have a big project like this, with some demands that were different than we had before the experiment, he wanted to make sure the engineers, and here are engineers, all of these were engineers, worked with scientists together so that you would not build a facility that wasn't adequate to the task. And that was a very good idea, because then the facilities were adequate to do the experiment. And that was a very important step. And, okay, I think what I'm going to do is I'm going to run out of time, because, what? Well, okay, well, you don't know that. But I want to give you a little feel for what kind of things affect the interferometer. Now, this is a little technical, and I'll look at you to see how many of you just don't look like you're interested. I mean, I look at, but what you're seeing is a plot of the following. This is H. That's the strain, but it's a spectral density of strain. How much H at each frequency? It's a spectrum of H. And what's over here is the frequency. And you can see the thing. This is now the sensitivity of the initial LIGO detector and what limited it. And you can see this. Here's the boundary of what limited it. This is where it operated, the initial detector. Pretty much just where we calculated it might do that. Back from the work that was done both by the people at MIT and the people at Garching. We did all the work that made these curves. We didn't need to do any more. And so what happens is here is this is the ability to read the light, how well you can measure with light. And the more light you have, the smaller this gets. This starts going down. That's called the phase noise or the shot noise. And in here is something which is because you're operating at room temperature. You have systems, the mirrors are warm. The mirrors are suspended by things that are warm. You have thermal noise, the same kind of thing that people who do biology, when they look in a microscope and they see the cells jumping around because they're being hit by atoms. You're operating at room temperature. Because you're doing that, everything shakes a little bit. That's called thermal noise. And that makes a contribution here. And then finally, this thing called seismic noise, which is you've already gotten rid of. And let me tell you, that's where this other factor of 10 to the 12 comes from. You and I are all sitting here shaking at 1 micron. Every one of us is jumping up and down at several microns. When the subway runs, it's probably a little bigger than that. So there you have to go. From 1 micron to 10, that's 10 to the minus 6 meters to 10 to the minus 18. You have another 10 to the 12 to go. And that is where the other trick comes, and we'll get to those in a second. But this has that trick in it. The reason why I'm showing you this curve is because there's a couple of things that are interesting in it. Right here is the reason why it costs so much to build LIGO. You had to get rid of all the gas. The gas, if you didn't take it out of the tubes, the gas would scatter the light, and it would make fluctuations. The number of atoms in the column was changing all the time, in the column of the laser. So you had to get rid of the gas. So that was expensive. The other thing, which is actually quite fundamental, and something that GEO has done a lot to help to get around, is this thing, which is not yet a problem, as you can see in this experiment, has become a problem in the new experiment. And that is, if you now look at what happens here, this I told you is the phase noise, the ability for you to measure where the position of the mass is. This is in your process of trying to measure where it is you disturb it. It's the Heisenberg microscope. In other words, quantum theory comes right into this with a macroscopic system. And when you want to measure the motion of a mirror, let's say that's quite massive, and it was 20 kilograms, now it's 40 kilograms. And if you hit it with light, the fluctuations in the momentum of the light, number of photons per second hitting the thing, cause the thing to shake around. And that's exactly what Heisenberg said. It would limit your ability to measure both the momentum and the position of a quantum system. We have exactly that problem, but now with a macroscopic system. And so that's this. That's called the radiation pressure noise. And this is the quantum noise. And part of the reason I want to show you that. And here is one other noise I want to tell you about, which is important because of LISA. And that is, even though you might have made, and you'll see in a second, the world's finest vibration isolation system to get rid of that shaking I told you about, you can't get rid of everything. And the reason is, there is those things in the ground that cause you to be accelerated with respect to the stars. Those are the shaking that you mean. And now it turns out certain things happen that you cannot do anything about. The fact is a ground wave comes along, and what it does is it makes the Earth a little denser here and a little less dense here, and that travels along. And let's say here is a mirror where that thing is, and that mirror senses the density change of the ground due to gravity between the mirror and that density change. That's just plain old Newton attraction, Newtonian attraction. And that, you can't shield that. You can't do anything with it. And that's called, I don't know what the hell the name is here, it's called gravity gradients. Now we call it Newtonian gravity. And that is one of the reasons why you go into space to do this. You can't get around that. And people are trying, but I don't think we'll succeed very well. Just when you look at how steep that curve is. Okay? So, all right. So here's the tricks that then, and I won't, we're almost to the discovery. So I can see that I'm going to get into trouble. And the thing is this, the tricks, this is a trick that is the way that you get rid of the ground noise and some of the thermal noise. You take, here's the mirror, and you suspend it by another mirror. These are pendula. And you suspend that by another mass, and you suspend that by another mass. And this was first tried out in GEO, this kind of suspension. And it allows you attenuation of the ground noise, which is applied way up here by these springs, right, these two places. The ground, that's where you attach yourself to the ground. And you get an attenuation that goes as the square of the frequency for each stage. So you can get huge attenuations, but depending on the frequency you're looking at and what the frequency of the pendulum is. So that's an important step. And now that is only part of it. And why I'm making a fuss about this is because the discovery that was made was critical because of this and because of this. The second one is a little more complicated. I'll just have to tell you how that works. You take that pendulum suspension and hang it from another system, which is an isolation system, which, by the way, that thing might be useful to people here doing biology or doing force microscopy. It's an isolator that has got the following property. How many of you have ever put headphones on that cancel the noise in the room and just let you listen to the music? Oh, a lot of you. Okay, yeah, it's a standard thing. That's exactly the same idea here. What you do is you use a seismometer. I won't go through all the details of it. There's a seismometer that measures the ground motion on a platform. And then you measure that, then you push on that platform to cancel the signal inside the seismometer. That cancels the motion of ground. And that's called an active vibration system. Without that, we would have not made the detection. Okay? So, and then what's over here is a curve for the current. This is now the second version of LIGO. And I won't go into this because I'm going to run out of time. But the thing that dominates, the same kind of curve as before. A lot of the curves are gone. But the thing that now dominates is a real problem, which we're not there yet, is that the thermal noise, this is the noise in the coatings. The fact there's sound waves running around in the coatings of the mirrors. And they are actually moving the position that the laser beam is determining as the endpoint of the mirror. That turns out to be a dominant noise for us. We didn't expect that. We now know it is, and that's something we have to fix. Okay, so there's the technology. I just want to show you this so you can see the progress and also the why what is so important. What these are, same kinds of curves, but now there's real data here. This is frequency, and this is, again, H as a spectrum. And so now you can see certain things. I'll show you. This top red curve right there is the curve that Virgo had. That's the other, we'll talk about that in a minute. It's the Italian-French collaboration that has a 3-kilometer system near Pisa. And they were running with us in the beginning. And then there is a curve that LIGO had. This is before we did the advanced LIGO, and that's this curve. And it's much worse. You can see it's at low frequencies. It gets very bad. And then this is the curve that made the detection. This is the LIGO is not yet, advanced LIGO is not yet where at design. And you can see something very spectacular, though. Here is that gigantic difference. See the green in here, from 100 hertz to about 30 hertz. And you'll see why that's so important in a minute. That region is where that black hole lived that was so important. And you can see there's a vast difference between where we were and where we had to be for this detection in the new system. And by the way, just so you can see this thing, we're not yet at design. The design for LIGO, advanced LIGO, is this curve right here. So it's another good factor of 3. And here is the design for advanced Virgo, which is not, they're working on this. They're trying to get that thing together, and you'll see why it's important in a minute. So this is about as far as we're going to get, that curve. and that curve, with what's advancing in the next couple of years. And there are curves in there I won't discuss, that are ideas for the future. Okay, so now let me take you to what really happened. So here are the two detectors in the United States, one in Washington State, and there's another one in Louisiana. There is Virgo, which is near Pisa, these are the three instruments that probably will have the sensitivity to continue making detections of what we have now detected. GEO, unfortunately, is too short, 600 meters, but it's the instrument that has done a lot of the development. As I showed you, they have developed a technique for dealing with the quantum noise. They've had a technique for hanging the masses. A lot of the ideas that have been put into the instruments came out of GEO. And here are things that are planned for the future. Namely, the Japanese want to make, and they're in the middle of it, building a detector inside the Kamioka mine. That's Kagra. And then there is an effort that has started in India using one of the detectors Ligo built. It's called Ligo India, placed in India. And this hopes to be running in about 2019. This hopes to be running in about 2024. Okay? And that then, why all of these detectors, I'll show you in a minute, they're important for doing the science. And we'll get to that. Okay. So let me quickly show you LIGO for a second. What does it look like? This is a very quick tour. Here you're looking at, that was Hanford. This is Hanford. There's the end building. These are the tubes that are inside of these as culverts. That's Livingston, all the trees around it. Here's what the tube looks like. It normally has insulation on it. We had to take that off because of mice causing trouble. And here are people working on trying to make a laser system work. And here's the control room for the system in Livingston, and people learning how to run the thing. So that's a quick tour of LIGO. Now, I'm going to get to the detection. The criteria for detection, and remember, you have to live with the legacy of Weber. That was the problem we all felt very, very seriously, and that we could not make a mistake. Now, you will make a mistake, but you try everything you can to avoid making a mistake. And so we had a lot of safeties put into this whole concept. And what they are, they're the three ideas. I'll just say what they are. You can read them for yourself. The very top one has to do that whatever you see, if you see something in Louisiana and you see something in Hanford, Washington, they have to be the same. They could be delayed because the velocity of light is the velocity of gravitational waves. They don't have to be exact, but they have to be within 10 milliseconds of each other. You don't know where they come from, so you have to, but you know that they have to be the same and within 10 milliseconds of each other. And that's number one requirement, a coincidence for the waveform. The other thing is it cannot be a thing that you would measure in a system that we have at both sites, where you have the environment being very carefully measured. In other words, you measure the size, you measure the ground motion, you measure the magnetic field fluctuations, you measure everything you can think of about the environment. I mean, many, many different sensors. And if any of these sensors show a signal simultaneously with the thing you think is a gravitational wave, that's it. It's out. It's vetoed. Now, we're not done yet. There are many, many signals within the interferometer itself. In fact, 100,000 signals that are coming out of the interferometer. It's a very complicated instrument. But if any of those that are relevant, for example, I'll give you some good ones. Laser frequency noise, the laser amplitude noise, the stability of the pointing system of the mirrors. Any of those have glitches or things that look like the gravitational wave you think is there, that cancels it also. So we tried as best to try to protect ourselves. And that was actually very important. And here's what we saw that one day, which actually was in September of last year, a little before the meeting here. But I couldn't talk about it at the time. And what it is these were the signals. I'll quickly walk you through these. These are in that wonderful paper that was written by the entire collaboration. And what it is this is a signal that was seen at Hanford. And here's what are these signals? The time is down here. It's very short. 0.2 seconds to, it's about 0.2 seconds, this whole thing. All of them have the same time scale. So this is quite fast, and there's not much there. There's noise right there, and there is the signal that's building up, and it comes to a big, large value, and then it probably is noise again. Here is what happens at Livingston. That's now Louisiana, and they're superposed on top of this one, slid by 7 milliseconds. You slide it by 7 milliseconds, otherwise they won't be on top of each other. And that is, in fact, the time it took the signal to go from Louisiana. And there are many, many places. There's noise. There's no way out of it. But there are places where these signals begin to be quite well. They're not dead on top of each other, and there are reasons for that. And then there's noise out here. Now, we get to what was done here by Bruce and by Alessandra. What happens is you try to match. Now, once you can get some estimates of what you're looking at, and we rapidly realized this, by the way, you were able to see these signals by doing nothing more than making a filter that looked like that. And I'll explain that filter. Since you use that every day, you listen to your radio. We made a little bit of adjustment for how much bass you would let through. That's so the attenuation for the bass, and that's rumbles, noise, low frequency noise, and we made a little. We got rid of the noise at high frequencies where there hisses and stuff like that. And that's this, and that's the filter that was used to make those waveforms. They affect the shape of the waveform a little, as you'll see in a minute. But the thing is, that's all that was needed to be done. You could see them by eye, these signals, and that's something we didn't expect. And they were enormous signals. And here then is a theoretical curve which is made up of both Alessandra's technique, which is analytic techniques, which is the dark gray part, and it stops just about there, and then you have numerical relativity coming in for the very end. And it turns out the match between the waveform that is calculated once you know the parameters and the actual waveform, the difference between them is this residual. And that looks pretty white. There isn't much structure in that. That's true for both waveforms. So that was, as you said, very important to the discovery, that we believed it. And then here is something which is the chirp that is, so when you look at the frequency content, what's the frequency of this wave, the different frequencies in it. And it runs, this is again the time, it's not the same frequency every time. You can see these things getting closer and closer. And what happens is that runs from about 30 hertz, that's the bottom of the piano, to about middle C, to 256. And that's this thing, and the color tells you how much energy there is at different wavelengths. And they're pretty much the same at the two. They're not identical. And because that's the detector sensitivities weren't identical. And so that tells you what the chirp was. Okay, and now here is what we now believe we were seeing. And this was in that initial paper as well. This is again now, but now it's all cleaned up, and that filter that I showed you has been taken out, and it looks much flatter. But the red curve is a numerical relativity curve, and the gray curve that's directly behind it is the analytic curve with analytic waveforms. And they are very much, they're on top of each other. And the place where you stop being able to use the analytic waveforms is at a place where the velocity of, this is now the relative velocity as a function of time of these two black holes. That's what they are. And you can see them up here. They're far apart, close. They almost make a new hole. And there they are, making a new hole. And the velocity, as they approach each other, gets to be amazing. It's the velocity of about 0.6 the velocity of light. So here are things that we now know weigh about 20 solar masses, 30 solar masses, and we'll see the numbers in a minute. And but they are moving toward each other and crashing into each other at something like 0.6 the velocity of light. It's almost like doing particle physics with enormous astrophysical objects. It's unbelievable. This is the, and that then was the final evidence that we felt, and we believe in it. Now this is what Kip Thorne's group at Caltech and Saul Tucholsky's group at Cornell, they made a movie of this using numerical relativity. And you can see the waveform down below, and you can see how they depict it as a function of time. There's a time, it's very short. And what you're seeing, these two black holes, what you're seeing is a picture in 2 dimensions here. And what you see is where the colors are red or black, the clocks have slowed down dramatically. And where these arrows get long, like inside the holes, there is enormous tension. If you went in there, you get torn apart. So it's the tidal term that's pulling you apart. And you can see that, and this is as things have progressed toward the point where they merge. And this is a numerical relativity calculation that was done, and they slow it down here, so you can see into the throat of these things as they're about to form a new black hole. And that whole affair, as we'll see in a second, used up 3 solar masses. This mass is equal to the sum of the 2 masses minus 3 solar masses. All those 3 solar masses went into gravitational waves. And that was quite spectacular, because when you look at the time that's associated with that, you get that the amount of luminosity, the brightness, the amount of power that thing radiated was outshone the universe for something like 0.2 of a second. Everything in the universe. Sort of amazing, that one collision. Now, I want to quickly show you the results of kinds of things that, a couple more, and that is how we did the data analysis for real. And that's important because you don't see this so easily. what you'll see, this is the first method that showed this to us was when we cross-correlated. We took the signal and the noise from one of the detectors and multiplied it by time-shifted signal and noise from the other detector. And I'll show you what that looks like. I mean, it's a standard technique. Here, and this is just using the two detectors separately, and you can see the two waveforms. One's moving under the other, and when they coincide, and you square the result of the product of the this cross correlation, you get a very sharp signal. And that's the first way we did it. And that's this point right that in a curve where you have signal to noise. In other words, the bigger this number is, the bigger the signal is against the noise. And there it is. There is that event. That was the historic event. Very strong signal noise of about 20. And I don't care which one of these you use. This is the number of events you would have expected just from random chance in the same time interval of this. And this is so way down off the charts. This would have happened in that apparatus once every 2 or 3 million years on its own. So it means very little. That is a real event. But that's not the best way to go looking at the data. And this is the other way. And this is the place where Bruce and Alessandra played enormous roles. And what it is this. What you now do is you do better, but it's much more consuming of computer time if you make a template of the signal, what you think it is. After you know enough about it, you make a whole bunch of templates, different masses, different properties of the black hole system, and you pass them through and cross-correlate to those. And that's it looks like this. It's the same thing, but it looks different, as you'll see. Now you take a template. You see the clean template right there being slid through this thing, which is the same thing. This is a signal now with all the noise. And now watch what happens down here. You get a very clean signal. And it's represented in the following thing. That same data is over here now. And there is that one that we talked about already. That's the big event. But lo and behold, there's another event right there. And maybe another one right there. And this is all, again, the probability, if they go down in the 10 to the minus 7s, of the probability of this happening by accident in that same run. So that is the template search, and that's the way you get the sensitivity. And now what we're seeing after that is this is the event. This is now the same thing, only drawn on a different scale. You can see that this is about 10 to the minus 21. That's the level of this is 10 to the minus 21 times 10 to the minus 21. This is the signal that we've already talked about. This is a signal which we're sure of, very much smaller. These are the masses. And this is the change in mass that's associated with when the gravitational waves. These are more sensible black hole masses. People, it's all kind of big, but these are black hole masses people had thought about before. These are the big guys. And this one is that marginal event, which we think is about 80%, 85% chance of being right. And that took 3 months. We had one event. If you include that one that's marginal, we had an event per month. And I don't think I want to go through this except to tell you about it because I'm running out of time. I really am. What is in these pictures is the kind of analysis you do on those waveforms with these templates. And what they tell you, for example, the one that's actually quite interesting is I can just say what these say. This says we can't tell you anything about the spin of the individual members. This tells you what the masses are of the two individual ones. This tells you the total angular momentum left in the system after you've had them collide with each other. In fact, mostly orbital angular momentum that's been converted into spin. And this tells you what we think, and this is the important one for this, is how far away this was. Since we know what they are, we believe Einstein's theory, we can tell you, once we know the mass of the system, we can tell you about where these sources are. And this is 500 megaparsecs. That means about 1.3 billion light years away. That's where these things are. You have now, and this is one nice way to remember this, you've seen about 1,000th of the size of the universe. The volume of the universe we've looked at is about 1,000th of it, and we've had 3 events. Let me have 3 instead of 2.5, okay? Makes the calculation easier. We have seen 3 events if you look into 1,000th the size of the universe. Now, if you improve the system by a factor of 2 in distance that you can look, you have not 2 times more rate, but 8 times more rate, because the volume goes as a cube of that 2. So instead of an event with a factor of 2, with that, we will get not 1 event per month, but something like an event per week. Well, not quite that, but close to that. And then if you improve more, you're still not, we have a whole lot of the universe still to look at. And as you make the detectors better and better. And here's the trouble with only 2 detectors. And this is a sky picture of where we think the sources are. And this is a standard picture the astronomers use, where this is the hour angle, and this is the declination. So for example, overhead here would be at 12 hours. So here we think that this is where the big source was. It came from the south, and we can't tell you much about where the other sources came from. It's just all over the place. And that's the trouble with only 2 detectors. Now, these are the people who made it happen. And these are people who are not sung heroes enough. The man who really got the thing going is Barry Barish. He was the second director of the project, and actually is the man who formed the collaboration. He was the one who had the courage to make the collaboration and deal with the complexity of 1,000 people. Okay? And then Stan Whitcomb has been a scientist on this thing from the beginning. He's a Caltech employee, but right from the beginning he's been the guy who's been part of it all along. Gary Sanders was the project manager for Barry, and these are people they hired who are very important. This man is the deputy director, Al Lazzarini, and Dennis Coyne is the engineer for the entire project. And now one more slide like that, and you'll see the faces get younger as we go. Here are the people who are spokespersons of the collaboration. The first elected spokesperson was Peter Salson from Syracuse. The next one was David Wrightsey, who happens also now to be the third director, and Gabi Gonzalez, who is the current spokesperson. And here are the other directors, Jay Marks, who started the idea of using LIGO India, and David Wrightsey, who was there when we made the detection. And this team of people are the people who are crucial to the thing actually going on at the sites. I mean, Dennis, you already know a little bit, he's the scientist, but these are people you don't know. You know, well, David Shoemaker, you know, he was the guy who orchestrated building advanced LIGO. This man is the guy Peter Fritschel is the guy who is in charge of the science and the technology of advanced LIGO. And these 2 people are the people at the sites. Valera Frolov is the guy who actually commissions the detector, and the team that makes the detector work in Louisiana, and Daniel Sigg is the person who does that at Hanford. These are real heroes, okay? And this is sort of a cute thing. What happened when we made the announcement in February, public announcement, and I got on the subway in New York, and lo and behold, I saw this. Scientists found gravitational waves in outer space. If it only were that easy to find an apartment in New York City with a walk-in closet. This was a couple of days after the announcement, and then in the New Yorker magazine, there was this little cartoon. This guy's talking to this guy. He says, "Was that you I just heard, or was it 2 black holes colliding?" Okay, I mean, that this should get into the public conscience so quickly was, to me, quite amazing. I mean, and now what the future gives. The future gives, and that is two things, a lot of things, but one of the most important things is those other detectors that you saw when I pointed to them. They will change. This is what we could do. These are on those same sky plots, sort of the era circles on the sky. And this is if we have, in this case, Hanford running, we used to have 2 detectors at Hanford. The second one doesn't matter. So it's Hanford, Livingston, and Virgo. If Virgo had been on, we could have done a lot better in positioning where it is, but it wouldn't be wonderful. But it would help enormously in terms of the era. Now, if you add to that LIGO India, so you have Hanford, India, Louisiana, and Virgo, all of them, this gets to be quite civilized, even for an astronomer. I mean, you tell an astronomer, go look in a region about the size of the moon. That's something that's possible. They don't like it. It's much too big an area, but it's possible. And so then we might be able to get to the point when people can begin to couple this field to the rest of astronomy. The only reason I show this is there are many other kinds of sources that we'll be going after. Pulsars themselves may radiate into it. Neutron stars, we're looking for those. We haven't found them yet. And there's all sorts of backgrounds we will see. This is a very rich field and may very well change the way, as Martin said, the way we look at the universe. But I want to just end with 2 things. And that is that this is sort of the spectrum of what you can expect in the next 20 years. And what I'm plotting here is all the different things that are going on in gravitational wave physics. And here's LIGO. What's plotted, by the way, is frequency. So you may not be able to read. That's 10 to the 4 hertz. That's the highest frequency. Down here is 10 to the minus 16 hertz. So let's convert that into times. This is 10 to the minus 4 seconds. And there's about 1/10 of a second. LIGO itself and the ground-based things can do in there. And the source of some of them you've seen. Here's the thing we're going to talk about in a minute. This is doing it in space. with a very elegant system that's called LISA, which has been worked on almost as long as LIGO. And it has its ups and downs as too. It's gone through a major down when the United States decided to drop it, even though it was highly recommended. But now the United States is trying to get its way back in, and the Europeans here, especially at the Max Planck, have maintained the faith and kept this thing going. And there you have all sorts of new sources, big black holes colliding, small masses going into black holes, wonderful tests of general relativity you could do with this. And then you might actually find, well, there's a sort of simple-minded source, which now maybe not so interesting anymore, but they're all over the place. There's simple stars like the one that Einstein might have calculated, white dwarfs in our own galaxy. They radiate copiously. Let me say something about LISA a little bit. Here's Carsten, who you all know. But here's the thing that went off just about the time we had that conference here in last year. And what they were doing is they were preparing a system which had in it a mock-up for the sensing for the motion of the relative motion of the satellites. And here's this thing being ready to be made launched. And I'll get to a picture of that that's a little more sensible in a second. What it is this. What the idea of that whole thing was to test the relative motion in a place that's at the Lagrange point of the Earth-Sun system, and a place where the gravity gradients are very small, and to test to see, and that's one of the places where you would put the LISA itself, and to test and see what kind of noise, how well could they make these. It's an interferometer right here, and the idea was measuring the relative motion of this test mass against that one. That was the idea, and they found something really wonderful, absolutely wonderful. Here's what they found. This is a different plot than we made before, but it's a plot of frequency. That's down here. Let's get the scales right. Here's 1/10 of a hertz. Here's 1/100th of a hertz. Here's 1,000th of a hertz. And here's 10,000. So the 1 hour right in there someplace. Periods an hour. And this is now the acceleration between those two masses, the spectrum of the acceleration. And here is what they had hoped for, that they would have called it a success if the noise had been there. Here's what they need for the actual mission. That. And here's what they got. This red curve is unbelievable. It's just absolutely wonderful. They don't need to do it. Well, they need a lot to do yet. But the point is, they've shown one of the biggest technology hurdles in this whole thing. Spectacular. Okay? And there are other two things that are going to happen in our lifetimes. Well, yours, not mine, but yours. And that is these two ideas. And there is another method that's entirely different than this, which is to look at a whole range of pulsars. You put pulsars, or you look at pulsars, fast pulsars, all over our galaxy. And you look at them with radio telescope, and you look at their periods, how the pulsation changes as gravitational waves travel between the Earth's antenna and those pulsars. And that gets you periods of gravitational waves with periods of years to fractions of a year. And that's an experiment that's going on right now. And you can do that from the ground. And lastly, there's this thing which is, I think, to me, one of the most miraculous of all the things, and that is to look at the cosmic background radiation. And I'll end there. The cosmic background radiation has in it, if you look at the polarization of the cosmic background, in other words, the way the electric fields point, if you look at the patterns of the electric field, you can, from that, determine what the density fluctuations were in the primeval background, and see patterns that come about because of gravitational waves that run through the plasma that was at that moment. Gravitational waves that would have come from the very instant that the universe got created. That to me is a sort of unbelievable idea. The vacuum fluctuations from that epoch could make gravitational waves and you could see them. And that is something that was reported on a year ago by the Weiss experiment. Unfortunately, they were somewhat corrupted by dust. And they're still trying. Many, many more people are doing this experiment. I'm hoping they will have a result. So, thank you.